welcome to your final lesson of e-learning physics for the 2016 semester, and we're looking at relativity to finish off the course. It's going to be quite a fun topic to cover for the 20 minutes or so. Early 1900s, Einstein was attempting to develop an all-encompassing formula that could tie elements of chemistry and physics together and explain forms of chemical change and energy. What this eventually led to was his theory of relativity and his famous equation was his E equals mc squared equation. However, one aspect that troubled him more and more was time and how time is perceived and fits into various equations. And he thought about it in these ways. Is time the same in all points of reference? He also thought about how do we perceive time? And Einstein's next question was, how is it used in formulas if it is not the same in all references? So this is a thought experiment that Einstein went through. And it came to, what is the problem between the frame of reference and time? in particular, if I had some physics cart on a flat surface, and I had some observer cart, we had a table on this cart, call this observer OS, by the way. We had a ball on that table that's on the cart, and we have some observer on the ground, movement. And if the cart moves forward, the ball, a table, will appear to move differently. Terraforming differently there, I just don't have enough space, depending on the frame of reference. But I forgot to mention one thing, we're going to call this observer on the ground OM. So the observer on the table, OS, is stationary relative to the cart. And this observer sees the ball and sees the ball move backwards and then fall to the ground. OM observes the motion of the cart and sees the ball move this way. Basically, he's going to see the ball is going to fall straight down. Since OM can explain the ball's motion using Newton's 3 laws, he is in inertial frame. And that is Einstein's theory of relativity. All physics laws are upheld in the inertial frame of reference. OS cannot explain the motion using Newton's laws. So he is in the non-inertial frame. So there's a problem with reference and time, which brings us to another scenario. We're all leading up to something really specific here. Let us suppose that we have a rocket. You're going to enjoy my great drawing right now. We have a rocket. And I have an observer or a person on that rocket. The observer has a gun and fires a bullet out of that rocket, and that velocity of that bullet relative to the shift is 300 meters per second forward. And this rocket is also going at a speed relative to the Earth of 1,000 meters per second forward. Have some person on the Earth that is observing all that motion. So the velocity of the bullet relative to the ship plus the velocity of the ship relative to the Earth would give us the velocity of the bullet relative to the Earth. The velocity of the bullet relative to the Earth would be 300 plus 1,000, which would equal 1,300 meters per second forward. And that makes a lot of sense. That's just common sense in an inertial frame of reference with our guy observing the motion. Here's where it gets a little bit tricky. What if we have that same rocket ship traveling at a different speed? Let's say the velocity of the ship relative to the Earth, with this person observing it on Earth, to be 0.1 c. C is the speed of light, and c is equal to 3.00 meters per, c is equal to 3.00 times 10 to the 8 meters per second. So that's the speed of the ship that it is going. We have this person on the ship again holding a flashlight. And it's shining light, so that tells us that the speed of light relative to the ship, because we have light going on, is 1 c. And there's our speed of light. If we were to determine the speed of the light relative to the Earth, we would get VLS, VSE, and that would equal 1c plus 0.1c, which is 1.1 c. But what's the problem here with the speed of light? The problem here that Einstein noticed is nothing can exceed the speed of light. In reality, this should not be any greater than 1.0 c. So this causes a problem in this case. This causes a problem. The laws of motion don't seem to apply in the frame of reference here. And this was Einstein's problem when it came to the light, speed, and time. In his thought experiment, we had an observer on Earth, and we had an observer somewhere else in 2 different areas. And each of these are 1 light hour away. And the observer from Earth is watching, and the observer from Earth says, well, let's say it's 12 noon right now. And there's one person on one of these guys' planets and another one over here. Let's say over here it's 12 noon, and over here it's 12 noon. If this observer was to travel to planet 2 at the speed of light, what would the time now be? The time on Earth, we know, in 1 light hour would be 1 p.m. What would the speed of light, or what would this guy's time be if we were to take a watch? Time would they observe? And that's the problem with light, speed, and time, and this is what Einstein was trying to do, was to get this encompassing formula that would relate the two. And he was actually able to come up with this. There is a derivation, but I'm deciding I'm just going to give you the formula right off the bat. Tm is the time, and as I'm thinking about it right now, you do need this formula for the exam. It's the time as seen by an outsider who observes the moving ship. Ts is the time as seen, let's call him a spaceman, in the ship. And that will be seen by the person as they are in the spaceship, the time that they see as it takes to travel at the speed of light to the other place, the other planet. V is the speed of our ship, and C is the speed of light. And this is where it gets really fun and really interesting, because this is dealing with the concept of time dilation. And the best example that we have of time dilation that we can study is what's known as the twin paradox. And let's see how this twin paradox looks. We have the Earth, and on that two twins. Please picture that these guys kind of look the same. My artistry work is not the greatest. And what's going to happen is this twin is going to get into the rocket. Twins, not both, just one. While the other twin is going to stay on Earth. And this twin that's in our rocket is going to take the rocket ship and fly to Alpha Centauri and back. Alpha Centauri is 4.4 years to get there and 4.4 years to return, traveling at 0.9 the speed of light. So it's easy to see here in this case the total time from the observer on Earth would be 8.8 years. And I did neglect to tell you that both of these twins right now are 30 years old. So that's easy to say that this twin that stayed on Earth is 38.8 years. But what about the twin in the rocket ship? How old would that twin be? Well, this is where it's handy to take Tm is equal to the time as experienced by the spaceman all over 1 minus v squared over c squared. 8.8 years is observed on Earth. We don't know what time that the spaceman has observed. Over 1 minus, this will be 0.9 over 1. We would have 0.9 c squared. We would have 1 c squared if we were to plug this into our calculator. But these two basically just cancel out, so we have 0.19, and 1. So 8.8 is delta TS all over the square root of 1 minus 0.81. And that gives us 8.8 is delta TS all over square root of 19, 0.19. So 8.8 is equal to TS over 0.436. So we can take 8.8, multiply it by 0.436, and that is 3.8 years. Which is telling us that if this twin who was on the rocket ship was originally 30 years old, this twin now perceives himself to be 33.8 years old. There's the twin paradox right there, both the same age. One traveled very, very close to the speed of light, and this twin, after traveling at the speed of light, is now actually younger. Do we perceive that as true ourselves as observers on Earth, where the paradox really occurs? Which one do we think? And really, that's how the course has ended. Like I said, you do need to know this equation for the exam. Try to follow through how we did it. No matter what, even if it's like say 0.5c, you will only take 0.5 over 1, so you get 1 minus 0.5.